Okay, good morning. So those of you who got here a little late, so Carmen, I'm going to go ahead and record the lecture, and I'm going to upload that on to Canvas as soon as it's done rendering. I'll get it up and load it into Canvas so that everybody will have this. Everybody will have the lecture for review. All right, so we ended up stopped talking when we're going over hydrolysis of salt solutions. So I think that was kind of the last thing we covered. So we had hydrolysis of, we'll say salt solutions. So hydrolysis of salt solutions, and we're just continuing this from where we left off. So we talked about, strong acid, weak base, or weak acid, strong base, weak base, and just kind of some concerns going into what type of solution we would have. So I'm not sure if so I'm going to recover it. I'm not sure if we talked about this last before we finished. So I'm just kind of going off memory what we had here. So we'll just start here. I think it's a good starting point. So we'll say salt of uh, weak base and a strong acid. So just kind of some terms here. So this is a salt of the weak base. So the salt of a weak base, strong acid solution. Right? So if we have a weak base and we have some strong acid, is that we get this conjugate acid plus we get this conjugate base. Right? Now, we can also look at it this way. We can also look at this compound as NH4 plus Cl minus here. And this is just going to be some ammonia chloride. All right, so that's just going to be some ammonia chloride. But when we look at this, we have our acid, we have our strong acid, weak base, and then we get this conjugate acid, conjugate base. And when we're looking at Cl minus, this is absolutely, a very weak, I don't even put very here, very weak base. And the case sub B here is, just almost zero at this point, right? So when we're looking at a mixture of a strong acid and a weak base, well, the result of that, this ammonium is what's going to react with water, right? So we're going to have ammonium plus some water, and that's really what's going to affect the pH, right? That's going to affect the pH, so we have NH3 plus some H3O plus, right? Is that the NH4 is going to produce some H3O plus, and essentially this is what's going to affect our pH. So when we're looking at salts of weak acids and strong bases, all right, Joe. I'm recording the lecture, so you don't have to record it anymore, and then I'll get it uploaded onto Canvas as soon as it's done rendering. So looking at the salt of a strong acid, weak base, right? So let's take aniline chloride, right? So we just did ammonium chloride. Well, let's take a look at aniline chloride. So let's say we put aniline chloride into a mixture of hydrochloric acid. So this is aniline. And then if we did, oh wait, no, we'll just take aniline for a second. So aniline plus hydrochloric acid. And now we're going to get the salt of a strong acid, weak base. So this is my strong acid. This is my weak base. Okay, so the salt of this, right, is going to be NH3 plus some Cl minus. And again, our Cl minus, even consider it, we can actually consider this a spectator ion, right? We're just going to consider that a spectator ion. So here when we're looking at a reaction now, so now let's take a look at a reaction, and this is what we're going to consider for our reaction. All right, so for our reaction we have, what is it, 6 carbons, so we have C6, we have 5 hydrogens, and then we have NH3 plus, right? So it's the same thing. So I'm going to actually just put an arrow here that this is C6 H5 NH3 plus. So it's the same thing. So when we're looking again at a strong acid, weak base, we need to look at the salt of that reaction, right? We're looking at the salt of it. So here we have the salt, and if we use that salt and we put that into water, well, let's see what happens to that reaction now. Well, now I'm going to get, if that's my conjugate acid, we're going to get C6H5 NH2 plus some hydronium, right? Aqueous, this is liquid, aqueous, aqueous, right? So essentially, and it's the same thing that we did before, right? So this is my salt of a weak acid, strong base, and we use this to determine our reaction here, right? That we use it here, we add some water to it, and we get our conjugate base plus our hydronium, and that's what's going to affect the pH, the hydronium. So here, this is what's going to affect our pH. So now we can say, so what if I propose a question here? We'll say, what's, I don't want to write it up there. I might have to rewrite the reaction, but I need to get this information here. So we can say, what is the pH of 0.233 molar, and I'm just going to write this, aniline hydro, gotta respell this. Aniline hydrochloride, right? If I give you this information here, aniline hydrochloride, right? Ammonium chloride. This is aniline hydrochloride, right? So what is the pH of this solution? Well, in order to figure out what the pH is, right, we're going to have to determine a couple things. We're going to need the Ka. We're going to need the Ka. We're going to need to determine our, I'm so sorry about that. Let me get these dogs under control. Hey, hey, knuckleheads. Come on. Come on. Hey, hey, hey. Shh, shh, shh. Come on. That's okay. If you see Simon around, can you just put him up here? Okay. Okay. All right. So we need to determine the Ka. or maybe not even determine it. We'll see if we need to determine it. We might just be able to find it. We needed to know the concentration. And from this, we're going to actually have to get that because I don't have the pH. If I had the pH, I could determine the concentration, but I don't have the pH. So we're going to actually have to do that from an ice table. So if we go to, let's see if we can find the Ka. Let's go to Appendix H. And Appendix H, we're going to look for aniline chloride. Appendix H. Let's see here. Appendix H. So Appendix H, we're looking for aniline chloride. And I've already drawn aniline. And if we remember the drawing of aniline, so here is the line structure of aniline chloride. So we have the ion structure. So here, if we take a look at that, we just kind of have to match that up here. Then we have hydrogens out here. All right, so we have this structure here. And if we take a look there where it says phenylamine aniline, so it looks like aniline. So what we have here is, because that's the ionization constant of a weak base, we have the Kb, not the Ka. So our Kb is 4.3 times 10 to the minus 10. So here we have a Kb value equals 4.3 times 10 to the minus 10. So 4.3 times 10 to the minus 10, and we have this Kb value here, right? So here, we can figure out what the Ka is, because we have this formula here, Kw equals Ka times our K sub B, and we know that the Kw is equal to 1.0 times 10 to the minus 10. So 1.0 times 10, I'm sorry, to the minus 14 is equal to, we'll put our Ka over here. We know what the Kb is, 4.3 times 10 to the minus, Ka to the minus 10. And now we can figure out what that Ka value is. So that Ka value, 1.0 times 10 to the minus 14 divided by, so we get 2.3 times 10 to the minus 5. So here is our Ka value. So now that I know what the Ka is, well, now let's go ahead and get our table here. So we have, I'm just going to rewrite the formula, C6H5NH3 plus our water at C6H5 plus our hydronium. So now that I know the Ka, we can come out with an ice table here, because I do have some initial concentration here of the aniline hydrochloride, right? So the aniline hydrochloride would be, even though there's no chloride here, this is what we consider our aniline hydrochloride here, right? Aniline hydrochloride would be C6H5NH3 plus Cl minus, right? It's a combination of this and this for aniline hydrochloride. But the only thing I need here, because the chlorine is just a spectator ion, is I'm just looking at that information. So this is the initial concentration of aniline hydrochloride. So if I draw my ice table, I have 0.23, the 0.0233, nope, it's 0.233. I don't do anything with water, 0, 0, minus x plus x plus x, 0.233 minus x plus x plus x, and my Ka is equal to 2.3 times 10 to the minus 5, and my Ka is a lot less than 1. So I'm just going to make an assumption here and just use 0.233 minus x. So if I use that value here, we can say 2.3 times 10 to the minus 5 is equal to x times x over 0.233. Once we know what this value is, so let's plug this into the computer, or not computer, but let me plug it into the calculator here. And this x equals 2.3 times 10 to the minus 3. So now we know what x is. So as soon as I find out what x is, that's my final concentration here. So my concentration, right? This is our concentration of hydronium. That's our concentration of hydronium. So we can say that H3O plus, this concentration is 2.3 times 10 to the minus 3. So what is the pH of that? Well, we can say pH is equal to the negative log of 2.3 times 10 to the minus 3. Put that into the calculator. Somebody have a calculation for that? 2.3 times 10 to the minus 3.
I got 2.63.
All right, so now we've figured out the pH of that. So again, I think the most confusing part of this entire thing is when we talk about the salt, and this is just really a key word here, the salt of a weak base and a strong acid. This is the salt of that. But because the chlorine is a very weak base, we're just going to consider this as a spectator. We're just going to consider it as a spectator, and this is what's really just going to affect the pH, right? That's going to affect the pH here. Because we're going to be able to make hydronium once we mix that with water. And again here, that's what we did. So here, taking another look at that, we talk about the salt of a weak acid, of strong acid, weak base. This is the information we need for the reaction, right? We do not use this reaction here in order to determine the pH. Is we have to come up with a new reaction that involves the salt of weak base, strong acid. And that's what we use to write our reaction. This is the salt of a weak acid, strong base, and we mix this with water, that's going to produce more hydronium, and that's what's going to give us our pH. So if we're given a problem like this, we do not use this for pH. You're never going to get an answer, right? You're never going to get an answer because right? We don't have any concentration of HCl. We don't have any concentration of aniline. So we need that conjugate acid there. Let's see. Let's do another one. So I think our next one is going to be the salt of a weak acid and a strong base. So let's do salt of a weak acid and a strong base. So weak acid, strong base. So if we take, let's take a weak acid. So we have, there's a weak acid plus a strong base. So here's a strong base. So weak acid plus strong base, and it's going to be a similar notion here. We're going to get this conjugate base, and we're going to get Cn plus some H2O. And you'll notice that I didn't write Na anywhere, right? Because again, just like the Cl minus, Na plus, right? This is also a spectator ion that doesn't have any effect on pH. Has no effect on pH.
And you know that automatically because there is no sodium in the product?
I'm not even going to give you the reaction. If I ask you a question on the exam, I'm going to tell you the salt of weak acid, strong base, a salt of strong base, I'm sorry, strong acid, weak base. It's up to you to determine this. You need to know, oh, this is a spectator ion, I'm not really concerned with it. This is a spectator ion, I'm not really concerned with it. What I'm concerned with is I'm concerned with the salt of a weak acid, strong base. This is my salt of a weak acid, strong base. So we're not going to use this reaction to calculate pH, to calculate Ka, to calculate anything. I just need to realize that this is the salt of my weak acid, strong base. Once I figure that out, then we're going to write our reaction to determine our ice tables, concentration, pH, the Ka, the Kb. If I take that salt of a weak acid, strong base, and I add that to water, the product of this is going to affect the pH. Is that here we're going to get HCN plus we're going to get some hydroxide. And what's going to affect the pH? This will affect pH. So this is the reaction that we're going to use for our ice table and any calculation we need. Is that if we're doing a salt of a weak acid, salt of a strong acid, we don't use this one. We do not, I'll even write it again, do not use for ice table or anything else. Like we do not use this. Do not use that reaction. The only thing we're doing with this first reaction is determining the salt of that reaction. Because the salt of that reaction is when we mix that salt with water, that's what's going to affect the pH. Does that help, Elisa?
Yeah, thank you.
Okay, so now that I have this reaction, because the only way we're going to be able to calculate pH, if we look at this reaction here, well, what do we need in order to calculate pH? Well, we need one of these two things. I need either OH, or I'm going to need this, or essentially this, right? If it's not in my reaction, how the heck can I calculate pH? Right? I can't. If we go back to the previous reaction, and I have this first initial one right here, well, how am I supposed to calculate pH from that? How am I supposed to calculate pH from that? Well, in order to calculate the pH, we use the salt of that reaction. We use the salt of the reaction, and we put that in water. And that will give us some concentration of acid, or it'll give us some concentration of base. The hydroxide, or the H3, or the hydronium. So let's see here. Do we have HCN here? I flip to it. Yep, we do. Okay, so we're going to need some information here. It looks like we have the Ka. So if we go here, we're going to look for HCN, and there's HCN. 4.9 times 10 to the minus 10. So the Ka is equal to 4.9 times 10 to the minus 10. Well, because our concentration here, because we don't have any acid in here. I don't have any hydronium acid. I don't have any hydronium here. What I have is I have hydroxide. So if we go to the previous reaction, because we had hydronium, we had to calculate the Ka. Because we have hydroxide, we need to calculate the Kb. So let's go ahead and just kind of do that off to the side here. So my Kb is equal to 1.0 times 10 to the minus 14 over 4.9 times 10 to the minus 10. So our Kb is equal to 2.0 times 10 to the minus 5. So now I know what the Kb is. So let's go with our ice table again. Do we have an initial concentration? Did I give it an initial concentration of this? No, let me give you an initial concentration. So we'll say concentration of is equal to 0.083 molar. All right, so we got 0.083. I'm going to drive a line through that. 0, 0, minus x, plus x, plus x. 0.083 minus x, plus x, plus x. If I look at the Kb value, can I make an assumption, yes or no?
It's going to be really small.
It's going to be really small, right? The Kb is a lot smaller than 1, which means that I really don't have to consider it for this reaction. So we can just say, 2.0 times 10 to the minus 5 is equal to x times X over 0.083 is that we can just make an assumption because KB is a lot less than 1. So here, X is going to equal 1.3 times 10 to the minus 3. Well, that's what X is. So I know what this concentration is here. So I know the concentration of OH minus is equal to 1.3 times 10 to the minus 3. Well, let's go ahead and figure out what the pH is. So pH is equal to the negative log of H plus. Well, we only have OH. Can we figure out what H plus is? Yeah, we absolutely can. So 2 methods in order to calculate pH. Why don't we just do them both? So we can go H plus is equal to 1.0 times 10 to the minus 14 over 1.3 times 10 to the minus 3, and that'll give us 7.7 times 10 to the minus 12. So then we can go pH is equal to the negative log of 7.7 times 10 to the minus 12.
I got 11.11.
11.11. So our pH is 11.11. The other way that we can do it is pH is equal to 14 minus the negative log of OH. So I'm just going to take the negative log of this value. So if we go negative log 1.3 times 10 to the minus 3, we get 2.89. 2.89, which means that I could just do 14 minus 2.89, 14 minus 2.89, and we get 11.11. So we still get the same answer regardless of which method we use. Right, so, it's really just important to determine what these spectator ions are going to be, right? Spectator ions just aren't really going to be considered because their Ka or their Kb value is really just almost as a 0 in a sense. So, when we have a salt of a weak acid, weak base, well, what's going to determine this is, well, if the Ka is greater than the Kb, or if the K sub b is greater than the Ka. If the Ka is larger, well, then this is going to be something that's going to be weakly acidic, right? This is the Kb is larger, we're going to have something that is weakly basic. And the spectator ions are just really unaffected. They just won't affect hydrogen. Let me just write that down as well. So we'll just say spectator ions won't they won't affect hydronium or let's see, or pH, right? So if we have something like LiOH, right? When this splits apart, we get Li here, plus we get some OH, is that here is your spectator ion, right? Calcium hydroxide, right? Here, spectator ion, right? That's not really going to be a concern of ours going into that. We can do it with, you know, something like this. How about something like this? If we go K2, is that we're looking at this, is that this is going to be my spectator ion. And we would consider this um, conjugate base. So if we have this in a reaction, we have CK2, CO3. We split it up here. We're going to have 2K plus we have CO, right? Is that we're going to consider this the conjugate base, right? Is that here I can put this in a reaction now. If that's what I'm looking at, I can say, well, how about we do right? And now I have my reaction. I have my conjugate base plus I have my base and my conjugate acid. Right? So we just kind of need to determine what these reactions are here, because essentially this is not going to affect pH. It's not going to affect the hydronium. It's not going to affect the hydroxide. Is that this, when put into water, will affect pH. How? Well, let's put it into water and see what happens. If that's my base, I'm going to get H, and there it is. I can now calculate pH from this reaction because now I'm going to be able to determine some concentration of hydroxide, and I'll be able to calculate some information about that reaction. Maybe we should do one with this reaction here. Since we have it up. How about let's just calculate, let's do that again. Let's go ahead and calculate pH again. So we'll go ahead and calculate pH of 0.25 molar solution of carbonate. Right, here's my ice table. I'll give you the K. I'll just give you the KB for this one. So the KB for this one is going to be 2.13 times 10 to the minus 5. So we have our KB value. So here, again, we have 0.25, 0, 0, minus X, plus X. You guys are going to be experts at ice tables by this point. Is my KB small enough that I can just ignore this X here? Yes, no? Do I have to involve the X or can I ignore it?
I think you do have to, because it's not that, well, it's less than 0, but it's
It's to the -5, which means my answer is going to be,
Oh my bad. Yeah, okay. Yeah, I got
right?
confused
It's
with
going to be
that.
pretty, that's a lot smaller than 1. So we can just go ahead and ignore that and just use this one because the KB is a lot smaller than 1. So we're going to have x times x over 0.25, and x is equal to 2.3 times 10 to the minus 3. So now that I know what x is, right, I know what that concentration is, so that I know concentration of hydroxide is equal to 2.3 times 10 to the minus 3. So the pH is equal to 14 minus the negative log of 2.3 times 10 to the minus 3. 14 minus negative log of 2.3. So my pH is equal to 11.36. All right. What was that?
I got that same value.
Got the same value? Okay, good, good. So now we can talk about, some of you may have seen this. You guys might remember this from 201. So from 201, we may have seen chemical compounds like this, where it would say like zinc, and then you see this big dot here, and then it would say something like 4H2O, right? This means this zinc has been hydrated, right? So what we'll talk about here is we're going to talk about is the ionization of hydrated metal ions. So what this essentially means when we see something like that, it just means that this really has something we call a solvation sphere, which means essentially we have 4 water molecules that are just, these are the first 4 water molecules that just kind of surround this zinc, right? So that's what it means. So these are what we consider hydrated metal ions. So essentially how we can imagine this is we can imagine it a little better like this. So we can say this is going to be zinc, still has a 2+ charge on there. So we're going to say zinc H2O4 2+, right? And it means the exact same thing as my drawing here. Zinc with a 2+ charge surrounded by 4 water molecules. So if we write a reaction for this, we can say zinc is that we can still put this in water. Just like we can put our weak acids in water, we can put our strong acids in water, we can put all this in water. We just always put it into water. So if I add this into water, and this is going to be aqueous here, put it into some liquid water. Well, this hydrated metal ion is going to act as my acid. Okay, so if I donate, so this is going to act as my base here. And if I add a hydrogen to that, I'm going to get hydronium. And here's the little, this may be a little confusing, is that I've donated one, oh, that's a little too small here. Let me write it off to the side here a little bit better. donates 1 hydrogen. So in order to write this, we're going to take a look at it. We'll say, okay, so we have zinc. I don't have 4 waters anymore. I only have 3. So we downgrade the number of waters that we have to just 3. And one of them is now going to be OH minus. And then I'm just going to reduce the charge on that and say that this is going to be plus, because now I have a negative charge on that. So now we have, and again, we can come up with some kind of a reactor, some kind of information. Let's say, let me give you the Ka for this. So if I say the Ka is 2.5 times 10 to the minus 10, and our concentration of the hydrated zinc, we'll say this concentration is 0.25 molar, right? The ice table doesn't change. We can still calculate pH. I can calculate KB if I needed to. Is that nothing about this changes? Is that we still do our ice table as we normally do. 0.25. I'm going to draw a line through water. This is going to be 0. This is going to be 0. Nope, sorry, my dog's getting a little rowdy. Minus x, 0.25, minus x, plus x, plus x. You guys are going to be sick of ice tables by the end of this. Plus x. And because I have the Ka, we can go ahead and set this up. 2.5 times 10 to the minus 10. Can I ignore this x? Is anybody confused when I ask you that? Like, do you understand what I mean? If because there's 2 ways to write this equation. I'm going to write them both ways. If we're looking at this is going to be one way we can write it. We can say x times x over 0.25 minus x. But if our Ka is a lot less than 1, then we can just solve it this way. 2.5 times 10 to the minus 10 is going to equal x times x over just 0.25. And our Ka value is definitely a lot less than 1. It's to the minus 10, right? If it was to the minus 2, to the minus 3 might be pushing it. But if it's something like 10 to the minus 1, 10 to the 2, 10 to the minus 2, I wouldn't make that assumption. But because this is to the minus 10, it's almost negligible and it's not really going to affect anything that we have here. So we can go ahead and solve that. So let's solve that. And we'll say our x value is equal to 7.9 times 10 to the minus 6. So that's the value of x, right? There's my H3. That's all I needed. That's all I need to calculate pH. pH is equal to the negative log of 7.9 times 10 to the minus 6. And this is going to equal 5.10. But this is how we deal with what we call hydrated metal ions, right? And I think the most confusing part is probably going from this to this. Is that we have to reduce the amount of waters by 1, and we have to add that hydroxy there. But what's going to affect our pH is simply just this is what's going to affect our pH. Oh, let's see, what else do we have here? More ice tables. Oh, definitely more ice tables. All right, so when we're looking at the Ka, right, just a little bit of review here. So Px is equal to the negative log of x, right? pH is equal to the negative log of h. So the pKa is equal to the negative log of what?
Would it be hydrogen? Frozen hydrogen?
Let's review here. Px is equal to the negative log of x.
Oh, negative log of
pH is
H.
equal to the negative log of h. pKa is equal to the negative log of
Okay.
the Ka. So now we're going to be dealing with something we call, in addition to pH, in addition to pOH, is something we call the pKa. So the pKa, and let me give you some values here. So just to get some better understanding here. So if we get some hydrated iron, some hydrated copper, some hydrated zinc, is that the pKa value here. So this pKa value is equal to 2.74. This pKa value is equal to 6.3. And this pKa value is equal to 9.6. All right. When we talked about Ka values before, the higher the Ka, the stronger the acid. The lower the Ka, the weaker the acid. And it's the opposite effect for the pKa. The smaller the pKa, the stronger the acid. The higher the pKa, the weaker the acid is. Okay? So let's do something that's pretty complex here. I'm going to give you a problem here that I've found. So we're going to say, what is the concentration of aluminum H2O, we'll say 5, in a 0.15 molar solution of aluminum nitrate that contains enough nitric acid to bring the concentration of hydronium to 0.10. And we'll give you a Ka is equal to 1.4 times 10 to the minus 5. So we need to figure out this concentration here. What concentration in a 0.15 molar solution of aluminum nitrate that contains enough strong acid of nitric acid to bring the concentration of hydronium to 0.10. Well, let's come out with some kind of formula first. So if I have the Ka already, that means that our product is going to be the hydronium because I have the Ka, right? So this takes a little bit of analytical thinking here. Is because I have the Ka, I know that I'm going to have H3O plus. So now I'm going to have to add, because this has hydroxide, this is where my Al H2O 5OH minus 2 plus is. Which means on the other side, I'm going to need water and that conjugate acid. Here. So now I have my reaction. And this reaction was based upon me knowing the Ka. Right? If I only knew the Kb, well, we'd have a much different reaction because I'd have to replace this with hydroxide, and then I'd have this over here. Like it would be a much different reaction given if I was given the Kb. I'm going to erase it, but let's write it. If we were given the Kb, if given the Kb, I know that I'm going to need some concentration of hydroxide. And because this already has OH here, well, I know that I'm not going to have that. Is that over here? I'm always going to have water over here. That's a given. And then I would have this over here. I would put Al H2O 5 OH 2 plus. So I'd have a much different reaction if I was given the Kb. So again, this reaction was written off of my information of knowing. Again, we always add water. Water's always just going to be here. Water will just always be here. Am I going to put the hydrated? I'm going to put the hydrated ion into water, right? But do I need to determine what the concentration of H3O is or the concentration of my OH is, right? So let me go ahead and erase this now. You guys can keep that for your notes though. All right. So we're definitely going to need an ice table. So we'll definitely need an ice table here. And that we given our Ka value, so let's see. So we have some initial concentration. AlNO3. So here my initial concentration is 0.15 molar. This is, and again, we have to take a look at this and determine our spectator ions here. Is that here, right, is that this is my spectator ion, right? That's going to be my spectator ion, and I know it's my spectator ion because I'm looking at some concentration of this hydrated aluminum. This is my spectator ion. So when it says the 0.15 molar solution of this, this is Al3 plus right here. Actually, I should put a 3 plus here. I'm sorry. So this is my Al3 plus. It's just been hydrated. So if I draw this, let me draw it up here. This is what it looks like. Al3 plus. Plus I'm going to have 6 water molecules right? So if anybody's going like, Alex, that doesn't look like, that's AlH2O6. Yeah, I realize that, but it's a hydrated metal ion. Here it is. This is my Al3 plus. This is not a spectator ion. This is a hydrated metal. This is my spectator ion. So here we have 0.15 molar solution of Al that contains enough nitric acid to bring the concentration. So I know what the final concentration is here. If I know what the final concentration is there, that value is going to be right here. To bring the concentration to 0.10, which means the rest of this can now be filled in. Ka, oops. So here, the Ka, what do we say our Ka was? Ka, I'll write it down here. Ka is equal to 1.4 times 10 to the minus 5, and the Ka is a lot less than 1. So when I write this, I'm going to say 1.4 times 10 to the minus 5 is equal to 0.10 times x over 0.15. So x is equal to 2.1 times 10 to the minus 5. So now I know what x is equal to. I know what this concentration is. It's right here. So the concentration of 2.1 times 10 to the minus 5. So kind of complex. Again, we have to decide what our spectator ions are going to be from these hydrated metals that we have. And that'll bring us to, I guess, what we could consider. So we've gotten hydrated metals. We do need to talk about what we call polyprotic acids. So polyprotic acid. So we have these terms polyprotic. So let me give you what monoprotic. So this is an example of a monoprotic acid where protic, proton, monoprotic, monoproton, right? We're just going to have one hydrogen there. And we could say, let's say the Ka is equal to 1.3 times 10 to the 6. Yeah, 1.3 times 10 to the 6, right? And we can have our reaction here. So HCl, if we put it into water, we're going to get some hydronium plus, we're going to get some Cl minus, right? So that's our reaction of a polyprotic acid. Then we're going to have, let's do a diprotic. So a diprotic acid is something like this. So we're going to have maybe 2 hydrogens on there. So here we have some sulfuric acid, and again, plus some water, and we're going to get some hydronium plus HSO4 minus. And we can actually consider this, we're going to call this we'll consider this what we call the first ionization. So that's going to be our first ionization. But we can use the conjugate base as our acid because this is going to be amphoteric, right? All right. So here I can write another reaction that says HSO4 because I still have a hydrogen to donate. If we put that in water and now that acts as our acid, I'm still going to get some hydronium, plus I'm going to get SO4 2 minus. And we'll consider this the second ionization. So we have our first ionization, now we have a second ionization. But because of the second ionization here, we're going to have two Ka values that we can call this Ka1. And this Ka1 for the first ionization is going to be, we'll say 1.3 times 10 to the 3, right? That's going to be the first ionization here. We can say that the Ka2 for the second ionization, 1.2 times 10 to the minus 2. The larger the Ka, the stronger the acid. We see that the Ka1, right? So this acid is a lot stronger than this acid, right? Because the Ka is larger. If we look at the pKa, the sulfuric acid H2SO4, that would have a smaller pKa value than the HSO4. So because we have two different Ka values, is that we can also look at it differently, not just between those two Ka values, but the actual calculation for the Ka. So for the Ka1, that's going to be our products over reactants. Concentration of hydronium, concentration of HSO4 over concentration of our sulfuric acid. And we'd be able to calculate the Ka1 from here. So here, the Ka2, let me put this in a 1, 2, right? Well, that's going to be based off the second ionization. And we see that that's different. Concentration of H3O plus, concentration of sulfate over concentration of HSO4 minus. So two different calculations here, right? The calculation of this is going to equal 1.3 times 10 to the 3, and this is going to equal what? 1.2 times 10 to the minus 2. So let's see here. All right. So now we have these two different Ka values. Okay. If we had 3 hydrogens, we call it triprotic, right? So we have monoprotic, diprotic, triprotic, right? Just a different amount, but these are all we consider polyprotic because they can have a different number of hydrogens there. So if we take a look at a problem, let's say this particular acid, H2S. So hydrogen sulfide is saturated in an aqueous solution of 0.1 molar. Well, let's calculate the concentration of hydronium. Let's calculate the concentration of HS, and let's calculate the concentration of S2 minus. All right. So we actually only need one ice table for this. So we don't just because because it's because it's diprotic, And because we're going to have a second ionization, does not require you to have to do 2 ice tables. As long as you understand this, as long as you understand this, and as long as you can come up with the reaction for the first and second ionizations, there's no need for a second, there isn't a need for a second ice table. So here we can say our original, we're going to have H2S. This is our first ionization. Plus we're going to put it in some water. We put in some water, we're going to get hydronium, plus we're going to get this conjugate base. Looks like a 5 here. So that's the first ionization. And off the first ionization, we're not even going to worry about the second ionization just yet. Let's do our ice table here. This is going to be 0.1, 0, 0, minus x, plus x, plus x, 0.1 minus x, plus x, plus x. So here's the beginning of our first ice table. Let's go and let's see H. Oh, there it is. Perfect. So here it is. We actually are able to find 2 of these are Ka values. So here, ionization constants of weak acids. So if I have both Ka values, let me go ahead and write both of those down. H2S. So let's see. Ka of H2S equals 8.9 times 10 to the minus 8. And the Ka of HS minus equals 1.0 times 10 to the minus 19. 1.0 times 10 to the minus 19. All right, that's good. Oh, there it is. All right. Is my Ka a lot less than 1? Yep, absolutely yes. So we can go 8.9 times 10 to the minus 8 is going to equal x times x divided by 0.10. So here x is going to equal 9.4 times 10 to the minus 5. So because I know what x is, I now know the concentration. I now know the concentration of H3O plus, right? Because these are, again, that's equilibrium concentrations. Equilibrium concentrations. So I know that H3O plus is equal to 9.4 times 10 to the minus 5. Could we figure out the pH of that? Yep, we absolutely could figure out the pH of that. I have no doubt. But we were supposed to figure out, so there's that concentration. I also know this concentration here because it's the exact same. So the concentration of (9.4 times 10 to the minus 5). The only thing I have left is I have to figure out this concentration. But all we did was figure out the first ionization. So this is the first ionization. Well, let's figure out the reaction for the second ionization because this conjugate base is now going to be my acid. So if I do HS, and this is going to be my second ionization, HS minus, plus we put it in water as normal, and I'm going to get H3O plus I'm going to get some sulfide. The Ka2 is equal to this concentration. H3O plus H3O plus times the concentration here over the concentration of, well, let's see here. Look at this. I know this concentration, and I know this concentration, and I also know this is the Ka2 right here. This is Ka1, this is Ka2. I know all this information. I don't need a second ice table here. Is if I rearrange this, the Ka2 times this concentration divided by this concentration is equal to, oh, wrong one. Right? And that's just algebra. This is just algebra that I rearranged this equation. So let's go ahead and fill in all of those values. We're going to say the Ka2, 1.0 times 10 to the minus 19. 1. Oh, is that right? 1.0, yeah. 1.0 times 10 to the minus 19 times this concentration of 9.4 times 10 to the minus 5 divided by the concentration of H3O minus, which is 9.4 times 10 to the minus 5. I don't even need a calculator because this is going to cancel out this, and that means that the concentration of S2 minus is simply equal to 1.0 times 10 to the minus 19. And I didn't even need a calculator. Right. So didn't need a second ice table, didn't even need a calculator in order to figure out the concentration of each one of those there. We're going to have time for Henderson-Hasselbalch. Yep, let's just keep going. As we get into buffers and how buffers work. So just how buffers work, right? If we have some, let's say some acetic acid, and we put it into water, we're going to get some hydronium, plus we're going to get some acetates. Oh, CH3CO. Let me redraw that. There we go. And if we were to look these up, the difference between acetic acid, so let's see, is acetic acid even in here? Let's see. Organic acid, formic acid. Ammonia. Oh, really, they don't give you acetic acid, huh? Oh, there it is, acetic acid. 1.8 times 10 to the minus 5. All right. So our Ka is equal to 1.8 times 10 to the minus 5. 1.8 times 10 to the minus 5. So our K is 1.8 times 10 to the minus 5. Our Kb, 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. That our Kb is 5.6 times 10 to the minus 10. All right. So here my Ka is greater than my Kb. Now, how a buffer works is that anything we add anything that we add will keep hydronium constant. That if I add a little bit of base, I'm still going to have a constant concentration of H3O minus, depending on which way this shifts, right? That if I add some acid, right, we're still going to see some here. So let's actually think about that. So if let's add, what happens if we add strong base? Add some strong NaOH base. Right? And we've talked about this before, and I know that it may be confusing, but we have talked about this. If I put in some strong base, the hydroxide will consume H3O plus. If I start to consume this H3O plus, I have to be able to replenish it. So if we put in a strong base, this H3O here, that'll start to consume it, but when we talk about percent ionization, so acetic acid is some like 1.5, 1.3-ish percent ionization. What that means is that 98.5% of this is undissolved. So if I put in a strong base and it starts to consume this H3O plus, in order for this buffer to maintain its pH, it has to maintain this hydronium. And because there's so much of left of this unionized that it remains undissolved, well, we're going to shift the reaction to the right in order to produce more hydronium. Because if this base starts to consume that hydronium, the only way for this buffer to keep the pH is to produce more hydronium. And it does that by ionizing more of the acetic acid. If we add a strong acid, so if we add HCl, a strong acid, well, we get H plus we get some Cl minus. And effectively here, we're going to end up shifting this to the right. If we add in more acid, or let's see, so if we can split this up. Let me see, let me write it this way. Cl plus H2O, right? And we get some H3O plus. We're going to get some Cl minus. If I add HCl, I'm going to increase this. And if I increase that, that means I'm going to increase the pH, but this is a buffer. And a buffer's job is to maintain the pH, which means that we have to keep the concentration of hydronium constant. But by adding a strong acid, we would increase this concentration. And if we increase that concentration, we have to shift the reaction. The reaction has to shift to the right in order to decrease that concentration. So we have to start making more acetic acid. We have to start making more water, right? Because if we don't, then our pH isn't going to be maintained, right? So let's look on one more problem here. Because we're talking about this already, We can do Henderson-Hasselbalch next week, or not, we can do that on Thursday, as well as start in with, we got to do Henderson-Hasselbalch still. You know what? No, because it's a shorter chapter. I think we can go ahead and just do this rest on Thursday. So we'll end it here. We'll end it here, and I will need to mark my notes here. Yeah, we'll go ahead and just end it here then. All right, so let me go ahead and stop the recording.